Hi, I'm Arindam Keswani and I welcome you all to this video where we will be talking about cryptography. So before we get down to it, in today's video we will be covering the fundamentals of cryptography and I'll be going deeper into the subtopics, namely the symmetric key. I'll give you a brief overview of the said topic, but the major focus of today's video will be asymmetric key, which we will cover in the later part of this video. So getting down to the details without further ado, cryptography is a concept in network security which states that plain text is converted to ciphertext before sending it to the receiver. So the first question that should come to your mind is, well, what is plain text? Alright, that's a good question. I'll answer it for you. Plain text simply means a message that can be read by anyone and tried to be made sense out of. Then you ask me, what is ciphertext that we're converting the plain text to? Again, good question. So ciphertext is the format in which we convert a plain text so that while someone might be able to read the ciphertext, they will not be able to make sense out of it. The nature of ciphertext is such that it is incomprehensible. So you might ask me, alright, I get what plain text is, I get what ciphertext is. Why do we need cryptography? To answer your question, I would like to introduce an acronym at this point. CIA. Confidentiality, integrity, and availability. So in today's video, our major focus will be confidentiality. And to explain this in a better manner, I would like to tell you a real world situation. In the world of internet, it is virtually impossible to shield our devices from the risk of hackers. Hackers who are trying to invade our privacy at any given second, hackers who are trying to steal information from us for their own benefit. So while it is impossible to not be exposed to hackers, the concept of confidentiality states that even if a hacker taps into your network, even if a hacker intrudes your device and gets hold of your data, he or she will not be able to make sense out of it. And this layer of security is owed to the concept of cryptography. Now, I would like to go further in this with the help of a diagram. Alright, let's get down to symmetric key. As discussed earlier, we will not be going into much detail. So let's start off by talking about the various protocols that are used to implement symmetric key. Now, the first one that I would like to mention is DES. The full form of which is Data Encryption Standard. Now this uses 56 bits to be implemented properly. The next I would like to mention is 3DES. Well, it's quite simple actually. The full form, it's, well, triple DES, Triple Data Encryption Standard. Now, it's quite self-explanatory. The size of this particular protocol will be 192 bits. And the third protocol and the last protocol that I would like to talk about today is AES. That is Advanced, and as you might have guessed it, E and S stand for Encryption Standard. Now the value of the size of which is quite variable. It could be 128, it could be 192, it could be 256 bits, and so on and so forth. Now, talking about symmetric key in general as a concept, it uses the concept of key exchange. The keys that you see here at the encryption end and at the decryption end, these keys are same. So the pattern that you use to encrypt the plain text is the exact same pattern that you use to decrypt the ciphertext at the receiver's end. Now, as a bit of bonus information, let's say your network consists of n nodes. So the total number of keys that will be required for you to implement symmetric key, the concept of symmetric key properly, will be NC2. And that's it for this video. As far as symmetric key is concerned, I would like to now talk about asymmetric key in further detail. Now, the challenge in symmetric key was that the key that was used by the sender and the receiver was same, so it wasn't exactly the most ideal method of adding security to our data. So we overcame this particular drawback by the concept of generation of public key and private key by every device in the network. Now these two keys complement each other in the particular device. So what we did was that we removed the concept of common key, identical key, and we assigned public and private keys for each device in the network. Let's say there is a sender device A and receiver device B. So there will be a public key and private key for sender A. There will be a public key and private key for receiver B. So the way we go about it, well, is to encrypt it with the public key of the receiver. Many theories were derived on how to implement this, but what the conclusion was that we encrypt the message with the public key of the receiver so that the receiver can decrypt it with their own private key. Now, why do we do this and not by any other method? We do this because the public key of every device is shareable. So let's say there are four devices inside a network, that is A, B, C, and D. And let's say I want to send my data from A to B. So the public key of B is shareable. So A, C, and D are aware of the public key of device B, but what they are not aware of is the private key of device B. Therefore, if I encrypt it with the public key, receiver B can always decrypt it with its own private key, since it complements the public key, as I mentioned earlier. And no other particular device will be able to comprehend the data or decrypt it on their own. Now the concept, the protocol that we use to implement this asymmetric key is the RSA algorithm, the full form of which is after the names of the people who constructed this algorithm, namely Rivest, Shamir, and Edelman. Now I would like to go into details of the implementation of this RSA algorithm, and I will do that by the help of a numerical. Now to save on a bit of time, I have already written the skeletons of the formulas. I will explain them one by one. So let's talk about the first line here. C is equal to P to the power small e mod n. Now we use this formula for encryption. So what is C? C is our ciphertext. We derive this from the plain text. Now how do we get this plain text? So our message that we wish to send is converted into an integer. This simply becomes our plain text. Now, as discussed earlier, for security purposes, the plain text is not enough. So we convert it to the cipher by using this formula which we use for encryption. Now to decrypt this particular message at the receiver's end, we use a similar formula, that is the plain text. We get the plain text again by C to the power D mod n. We use this for decryption. Now we'll get to what D, E, and N mean as well. Now for this procedure of implementation of the RSA algorithm, we firstly choose two prime numbers, P and Q. Now for our example, we will be taking P as 17 and Q as 11. Now N is the product of P and Q. This is 17 into 11. This turns out to be 187. Now I would like to introduce a new variable here. This is known as theta. So theta, the value of theta is P minus 1 into Q minus 1. This simply becomes 16 into 10 is equal to 160. Now, when it comes to D and E, which we saw in the earliest formulas, there's E here and there is D right here. So D and E are calculated by this formula. D into E is equal to 1 mod theta. Now, for this example, I'm going to choose my E as 7. So the value of D after calculation turns out to be 23. For your own practice, feel free to do this calculation. It's quite simple. D comes out to be 23. Now all that's left, now we have all the variables. All that's left is to check whether the plain text that we are sending is received at the end in the same manner. Now, for our example, I would like to look at my converted message as the integer value of 88. That is, the original plain text value is 88. Now we'll convert it into ciphertext by this formula. C is equal to 88 to the power 7 mod of 187. Now we just have to simply input the numbers in the formula and get our output values. Now after calculation, the value of C turns out to be 11. And now this is our encrypted data. That is our ciphertext. Now that we've encrypted it, we send it to the receiver, where we will check whether the plain text that we receive is the same as what we sent earlier. So P is equal to C to the power D. In our case, C, as we just calculated, is 11, and D, as we calculated earlier, is 23. So that's 11 to the power 23 mod of 187. That is our N, as we discussed in the formula earlier. And after calculations, we find out that P is 88, which is the same as the original plain text value that we sent in the form of an integer. So we see that the exact same value is received at the receiver's end, and that's how we implement the RSA algorithm. As bonus information, as we discussed in the case of symmetric key, if we have n number of nodes, then the total number of keys that we require to implement our asymmetric key and in turn our RSA algorithm will be 2 into n. And that's it for this video. I hope all of us learned something from it, and I hope I see you in the next one.